Backens. She will talk about the stabilizer ZX calculus. Go ahead.
So this is basically a sequel to a talk I gave at QPL 3 years ago, but don't worry if you weren't there then or have forgotten what I've talked about. In the meantime, I will recap all the important details again. So first, let me unpack what it is that I'm talking about. So the ZX calculus is this graphical language for talking about quantum computation. Most of you have probably come across it before, sort of diagrams of red and green dots. And completeness is the property of a formalism that any equality that you can derive in sort of some other standard formalism, say in matrix mechanics, can also be derived using the new formalism. So in this case, any equality that you can derive using matrices, you could also derive using diagrams if the formalism is complete. And that's what I'm trying to show here. So stabilizers we've also heard about quite a lot in previous talks here. So I'm only looking at the ZX calculus for pure state stabilizer quantum mechanics here. And the specific thing that I'm trying to show completeness for is scalars in the stabilizer ZX calculus, because the previous completeness proof that I have for the stabilizer ZX calculus was only for a version where equality is, sort of in the matrix version, equality is taken up to scalar factor. And basically the way that ZX calculus that I used was constructed completely ignored all the scalars. And so while you could kind of show equality between operations up to scalar factor, you couldn't do anything like calculate amplitudes or probabilities. And I'm now putting the scalars back in so we can do that graphically. So the structure of the talk, I'm first giving some background information, including recaps of the stuff that I talked about 3 years ago. And then I'm going to show you how to modify the ZX calculus so that it keeps account of scalars, where beforehand it used to forget them. And then I will give the new completeness results, and finally some conclusions. So first, a very quick recap of stabilizer quantum mechanics. So rather than kind of considering all unitary operations and pure states, we're just looking at these, well, not just, I mean, obviously we're not just having unitary operations, we have state operations. And we have this group of Clifford unitaries which are generated by the S gate, the Hadamard, and the control knot. And then again, we do measurements on a computational basis. And everything I'm going to say is only about the ZX calculus for this fragment of quantum theory. So a ZX calculus diagram, as I said before, is kind of composed of these 3 different types of elements. We have these green and red things called spiders, because they have many legs. And we have Hadamard nodes which always have exactly 1 input and 1 output. So diagrams go from bottom to top. Things at the bottom are inputs, at the top are outputs. And our spiders also have these phasors associated with them. And in the stabilizer case, the phasors are always integer multiples of pi by 2. I'm going to denote the map that takes diagrams into matrix representation by these double square brackets. And so the green spiders are certain maps in the computational basis. The red spiders are the corresponding maps in the Hadamard basis, and the Hadamard nodes unsurprisingly map between the two. We can use these basic elements to build more complicated ZX calculus diagrams by either putting things side by side, which corresponds to taking the tensor product of the matrices, or we can connect up inputs and outputs, which corresponds to matrix multiplication. And there are certain types of specific ZX calculus diagrams. So a diagram that doesn't have any inputs is a state. A diagram that doesn't have any outputs is an effect. And here we're specifically interested in scalar diagrams, so that are diagrams that don't have inputs or outputs. So they can be as complicated as you like. They can consist of lots of nodes connected up together, like in this case. They could also just be a single spider with no inputs or outputs. And there's also another very simple scalar diagram, namely the empty diagram, and that just represents the identity scalar, so the number 1. I'm also later going to talk about another specific class of ZX calculus diagrams called zero diagrams, and those are just the diagrams that translate into zero matrices. So zero diagrams can be scalars or not, because you can have zero matrix in any dimension. So a zero matrix is just a matrix where all the entries are zeros. And so as one example, we could have this green spider with phase pi and no inputs or outputs. According to our interpretation map, that goes to this formula, where we now have this zero-fold tensor product, and we're just going to define the zero-fold tensor product of any normalized Brauer to be 1, and that's consistent with the other rules of the ZX calculus that I'm going to come to in a bit. And so this thing is just going to be 1, the first summand, and the second one is -1, so overall this diagram represents a 0. So I've told you how to construct ZX calculus diagrams and how to translate them into matrices, but in order to do computations graphically, what we need are rewrite rules that allow us to transform diagrams into other diagrams. And these are the rewrite rules of the scalar-free ZX calculus, so the version where we forget scalars. And in fact, we have this one explicit rule that says anytime we have a scalar that isn't zero, we can just ignore that, so we drop that from our diagram. We have another implicit rewrite rule saying only the topology matters, so that's something that's also come up quite a lot when people have talked about these graphical languages. So if you have sort of curved wires, you can just straighten them, and that's still, the diagram has the same value. Or you can kind of move components around in your diagram as long as the connections between them remain the same and the components remain the same, then that's also still the same diagram. And in addition to those two implicit rules, we've also got this list of explicit rewrite rules. I don't expect you to remember all of them if you haven't seen them before, but yeah, that's basically just to give you an overview. So the most famous one is probably this first one here, the spider law. So if we have two spiders of the same color that are connected by at least one edge, then they merge and their phases add. And that means that anytime we have a diagram that contains this as a sub-diagram, we can just replace that with the other side, and in that way derive an equality between two diagrams. So completeness, as I mentioned before, is this property that any equality that we can derive using matrices, we can also derive in the graphical language. So writing it down mathematically, if we take the interpretations of two diagrams and those are equal, so in the case of the scalar-free calculus, this equality between matrices would be up to scalar factor, then we want to be able to show, using the rewrite rules of the calculus, that the two diagrams can be rewritten into each other. And what I talked about 3 years ago was that the scalar-free ZX calculus is complete for stabilizer quantum mechanics. So I showed a way of taking an arbitrary non-scalar diagram in the stabilizer ZX calculus, bringing that into some sort of normal form, which is not actually unique, but which does allow equalities to be derived straightforwardly between two diagrams that are both given in this normal form. And in that way, any equality between arbitrary scalar-free stabilizer diagrams can be derived. So as long as this corresponds to a matrix equality that holds up to scalar factor. So that's it for the background. I'm now going to move on to putting the scalars back in. And so first, this is again the slide that I showed before about the rules of the ZX calculus without scalars. And we're going to have to modify those rewrite rules. Obviously, we want to get rid of the ignoring the scalar factors rule. But also some of the explicit rewrite rules actually only hold up to a non-zero scalar factor. So if we want to keep track of scalars, we're going to have to change them in this way. So these first two rows of rules just remain the same. They were already correct. In the third row, those rules, they were originally actually introduced in this form in which they're written now, but then later people dropped the normalizing factors because it was easier to do rewrites without those pesky scalars floating around, and I've just reintroduced them here. And those two rules at the bottom, which have slightly more complicated forms now, those are the rules that are correctly normalized, but where there's a phase, a complex phase between the two sides of the equality in the previous version. And those were originally introduced in the scalar-free form, and I've actually added the scalars from scratch to those two rules. So these are the new rewrite rules of the ZX calculus with scalars, and so that those now hold for equalities that we could derive accurate.
Sorry, what is that numerically, when you put brackets around, what is that scalar with the red dot?
So the one with the red dot and the green dot is just square root of 2. And this one is e to the I alpha times square root of 2, which is why we have another square root of 2 on the other side to normalize it again. And this one is e to the I pi by 4, or minus e to the I pi by 4, I think, times 2. So we have 2 copies of the square root of 2 on the other side. So if we're now keeping track of scalars and using the scale rewrite rules, we can derive a couple of corollaries about the original completeness proof. They were kind of implicit in the original proof, but not properly stated there. But we need an extra assumption, namely the assumption that every non-zero scalar diagram has an inverse. And the reason we need this assumption is that previously, so there are cases where previously we could just apply a rewrite rule, where we now can't apply it because we're missing a scalar. So the copy rule, which is this one, which used to be defined without this scalar here, if we have the scalar-free copy rule, we can just rewrite this Y-shaped diagram into two separate states. But because we now need the scalar here, we couldn't rewrite the Y-shaped diagram on its own, unless we have inverses. because in that case, so assume that this node labeled S here is an inverse to square root of 2, which in diagrammatic form just means that if we put those two diagrams side by side, then they equal to the empty diagram, which has the value 1. And if we have that, then we can take the Y-shaped diagram. Then, because any diagram contains the empty diagram as a subdiagram, we can just add square root of 2 and its inverse to our diagram, and then we have all the things we need in order to apply the copy rule. So that's why we need this assumption that scalars are invertible, and later going to show what we need to do in order to actually get these inverses. But for the time being, assuming that we have inverses, we can show that any stabilizer scalar diagram can be decomposed into disconnected segments containing at most 2 nodes. So either we have, so any scalar just consists of kind of tensor products of diagrams that are either a single node or one red and one green node connected up together, and they can have arbitrary phases. And the second corollary, which is particularly important, because a lot of the time we're talking about non-zero diagrams. So can we actually recognize whether a diagram is 0 or not? And the second corollary tells us that yes, making use of the first corollary, we can recognize when a scalar diagram is 0, and that's exactly when it contains one of those components in its decomposed form. And we will see later that obviously there aren't like 4 distinct diagrams that all represent 0 and equal to each other. That would be silly. In fact, we will show that we can rewrite those 4 diagrams into each other, and so there is just one 0 diagram where all the 0 scalars are equal to each other. So I've said that so I've assumed that we have inverses for all our non-zero scalars, but in fact none of the rewrite rules that I gave previously match the empty diagram. So using just the previously existing rewrite rules, we can't derive any inverses for scalars. And so we're going to have to introduce some new components for the ZX calculus. So I'm going to introduce this new node called the star node, and which is defined to be inverse to the single green node, so the star node has value half. This is for slightly technical reasons. Now we have this new rewrite rule, star rule, which does match the empty diagram, and that allows us, as I will show later, to in fact derive inverses for all non-zero scalars. So in particular, what we can derive is that this equality down here holds. So the inverse for square root of 2 is just the star node and another copy of square root of 2, which makes sense, seeing as the star node has value half. So that was the modifications that we need to make to the ZX calculus, and now going to move on to the actual completeness results. So first, let's just look at non-zero stabilizer scalars, so just diagrams that aren't 0 and that don't have any inputs or outputs. And for these diagrams, we can define a unique normal form, which is slightly complicated. So it consists of one element of this 8-element set, which includes the empty diagram, combined with some number of copies of either the square root of 2 scalar or the 1/2 scalar, or one copy of square root of 2 and some number of copies of 1/2. And this is a normal form, which means that we can rewrite any non-zero stabilizer scalar into this form. And we can also see that it is unique because the stabilizer scalars are just numbers whose absolute value is some positive or negative integer power of square root of 2, and whose complex phase is some 8th root of unity. And these diagrams in this set correspond to the 8 different complex phases. Those scalars here, those are all real, so those give us the correct normalization, because these diagrams up here aren't correctly normalized. And in this way, it becomes clear that this normal form is unique, and also it becomes clear that any non-zero stabilizer scalar does have an inverse, because if we take any one of these diagrams, we can construct its inverse by kind of taking the phase that gives us the opposite, this diagram from this set that gives us the opposite phase, and then also taking the correct normalization that is, again, the inverse of the one that we had previously. And then if we put the 2 diagrams together, because this is a normal form, because it's unique, that means that we then have to be able to rewrite this new diagram into the empty diagram, which is the unique normal form for the number 1. So we can combine this completeness result for non-zero scalars with the previous completeness result for stabilizer diagrams that weren't scalars in the following way. So we first just apply the same procedure as in the completeness proof for the scalar-free stabilizer calculus, except this time we use the scaled rewrite rules, and we keep track of the scalars sort of on the side. Because we have inverses, we can still apply all the rewrite rules that we previously applied. But we just focus on the non-scalar parts to start with, and either we can derive that these two are equal up to a scalar factor using the original completeness proof, or if they're not equal up to scalar factor, then obviously the full diagrams cannot be equal. And after we've kind of applied this process, we then look at all the scalars that we've kind of just put on the side, and we bring those into normal form. And then by combining the result on the previous slide with the results from the previous talk, that means that the resulting diagrams here are, so we can bring two scaled stabilizer diagrams into identical form if they are equal, and if they are not equal, so if they don't represent the same matrix, then obviously there is no equality to derive. So we're done. And by inverting some of those rewrites, if we can rewrite two diagrams to be identical, we can also rewrite one into the other, and thereby derive the equality that we want to derive. So, so far I've only talked about non-zero diagrams, and I've told you that we can recognize zero diagrams, so it's kind of okay to focus on the non-zero ones. But to have a proper completeness proof, obviously we want to look at zero diagrams as well. And in order to deal with those, we're going to need another couple of new rewrite rules. So the first one is this zero rule, which was suggested by Alex, which just allows us, if we have this zero scalar here next to an identity wire, we can kind of disconnect that wire. And then in the scaled case, I've also introduced this zero scalar rule, which allows us to drop scalars that consist of a single node if they're multiplied by zero. And because we can use this rule to disconnect any scalar consisting of two nodes, this one zero scalar rule is in fact sufficient. And using those two rules, we can now define a normal form for zero diagrams in the stabilizer ZX calculus. So there is just a single zero matrix for each number of inputs and outputs, so there's just one n by m matrix that's filled with all zeros. So there should be exactly one normal form for that's just determined by the number of inputs and outputs for zero diagrams. And so the normal form that I've chosen is this one here, so we have one copy of the zero scalar, and then we just kind of disconnect all the inputs and all the outputs with these green nodes. And we can rewrite any zero diagram into this form, and it should be fairly obvious that this is in fact unique. And therefore the ZX calculus is also complete. The stabilizer ZX calculus is also complete for zero diagrams. This doesn't necessarily apply to more general diagrams, because the being able to recognize zero diagrams only applies to stabilizer diagrams. Right, so for the conclusions, so previously I've talked about how the ZX calculus is complete for stabilizer quantum mechanics, but this was a completeness proof that ignored scalars, so equalities could only be derived up to scalar factor. And I've now modified the existing rewrite rules to be exactly true, not just up to scalar factor. I've added a new node, the star node, and 3 new rewrite rules. And using those, I've shown that the ZX calculus is now fully complete for stabilizer quantum mechanics with scalars. So in particular, we can now compute amplitudes and probabilities graphically. And there is a nice example of how to do that in the paper, but unfortunately I didn't have enough time to put this in the talk. So you're going to have to read the paper for that. And as further work, obviously, there's the question of the ongoing work of trying to extend the completeness result to larger fragments of quantum theory. So we know the stabilizer ZX, we know the ZX calculus is incomplete in general, but this incompleteness proof doesn't stop us from deriving completeness results for smaller segments of the theory, including approximately universal groups like the Clifford plus T group. So work is ongoing on doing that, and then obviously it might be easier to derive a completeness proof ignoring scalars first, but then it would be nice to also put the scalars back in if we manage to do that. Thank you.
Some questions?
This is actually a comment. During one of his talks, Scalars said he wanted to see an acclimatization of stabilizer quantum mechanics. So this is it. That's what this thing says.
this is an axiomatization. What are the axioms?
Well, I mean, this was processing, not mine, but I guess, yeah, I mean, you've got your components, and I guess the axioms would be the scale rewrite rules. So, take a while. So these ones plus the new rewrite rules that I've introduced later.
Why did you take star to be a half rather than 1/2?
Yeah, this was slightly for technical reasons because I couldn't figure out how to derive the fact that the green node is equal to 2 copies of this square root of 2 scalar the other way around. I have since figured out how to do it, so I could redefine the star rule to be 1 over square root of 2 rather than 1/2. But yeah, at the time it just seemed the most straightforward thing to do.
You still have this issue with non-unique normal forms, right? Which sort of inherited from the previous, so I guess that's why you didn't focus on it. So in the general case now, diagrams with scalars, you've got 2 diagrams, you want to know if they're representing the same, then you out.
Yeah.
Stabilize a fragment. So what exactly do? You apply your rules, so you get normal forms of both sides, but normal forms aren't unique. So how do you do that final step?
So yeah, so the first thing is to just focus on the non-scalar parts first. And yeah, so you bring them into this GSLC form, which is not unique. But there is a process that, given 2 GSLC diagrams, rewrites them to be identical if possible. And if it's not possible, it will just stop at some point.
You have those rewrites to your rules and then have a confluent system.
I mean, this process does follow from the rewrite rules, but it's so it involves local complementations, which are kind of global rewrite rules on your GSLC form. They can potentially change the entire diagram, and therefore it's not very straightforward to kind of yeah. You can't just do them in the same form of sort of cutting out a small chunk and pasting something new back in, because you have to take into account the entire diagram. So yeah, that's kind of
that's a shame.
a bit tricky, yeah.
Is there some reason to expect that there wouldn't be some other set of rewrite rules that would allow everything to work in the confluence? Is it essential that it's got this nature?
No, I mean, like, Peter actually showed that there's a sort of presentation of Clifford circuits in terms of generators and relations that does allow you to bring things into a unique normal form, but that doesn't work very well for the ZX calculus because it's kind of, you have to find like new gates that aren't exactly these ones. And so, and also I think in some cases sort of twists are actually like meaningful as part of different operators, swap gates, which again in the ZX calculus those aren't very meaningful because they kind of just float around the diagram and just move things around. So yeah, it's not clear how to translate this into the ZX calculus.
Any other questions or comments? Yes?
Have you tried to extend this to QDIN stabilizer?
No, I haven't yet. I mean, there is ZX calculus for QDID, but I've not looked at completeness properties for that.
But someone at last year's QPL did, right? Did Jan talk about that?
Yeah, Andre is going to talk about, I think, QDID ZX calculus, but yeah, I'm not entirely sure.
Okay. Well, we're just on time, so it's a lunch break now, and thank you very much again.